Okay, I want to review the runtime problem that we looked at. And here I show it where we're asked to find the runtime t of n for a call to foo nums. Therefore, we're looking for the accurate running time of this method here, foo. Now, in order to look at that, we need to look at all the functions that foo calls, in particular goo and who. Exactly what is computed by this is not really important. We can just use our rules for dealing with sums and come up with a reliable, fairly accurate answer, and then ultimately we would find the big O of that answer. So let's go ahead and look at this. We need to determine what n means. I was pretty explicit here that this varies depending on an array A that has n elements. So I associate n with the length of the array A that I've underlined there. So my runtime t, let me just go ahead and write it over here, t of n, and I can express that by looking at the elements inside foo and breaking it down. So I'll start at the top, and you can see that this executes once at the beginning of the loop. This executes at the very end of the loop, even though the loop itself is not executed, because of course it's false. And then finally we have this return statement here. So I would say that there are three things outside the loop. The loop itself appears to go from the length, which I associate with n minus 1, all the way down to the point where I equals 3. At the point where I equals 3, it bails out. It's going backwards, whereas our mathematical sums go forward, but that's not really a big deal. From the runtime perspective, then, this loop is iterating when I is 4 all the way until I is n minus 1 inclusive. And I will write that like this. And now I just need to find the running time of all of the stuff, basically, that's in this loop here. Well, let's go ahead and look. We clearly have this executing every time and that executing every time. That's 2. We also have this executing every time. That's 3. On the other hand, we have to decide which is worse, this branch or this branch, that is, the call to goo or the call to who. If we look down here, we can see that the call to who involves an array A, which in fact is the same array A up here, so it's going to vary. That is, it's going to vary as A gets bigger, because we have a loop here that depends on length, which is basically n. On the other hand, who down here, while it's true that it has a parameter that depends on A, the actual computation is over a fixed number of iterates, I equals 0, 1, and 2, so it'll always be constant with a runtime of however much is done in this loop. By the rule for sums of big O's, we know that this will be much smaller than this. And given the way in which we calculate conditionals in worst case, we therefore want to work on this one and pretty much ignore that one. So as I said, we've got this runtime in the loop, and in there, what's going on is 1, 2, 3, and then the call to goo, which I'll call t sub g. The call to goo depends on two things, both the length of the array n and this parameter I. So that's my complete runtime right here. Now I just want to figure out what my t sub g is. So I'll go all the way down here and figure that out. But I'll write it up here. The running time of goo, as I've said, depends on I. Now, what's I here is called j here. So I'll go ahead and stick with the notation that I have. And now I simply want to find out what this running time is. Well, outside the loop, I have this, and I have one of those. right? And so I basically have two things outside the loop. Within the loop, I have a loop that's kind of interesting in that we set up something and then j increases until it gets up to that top value, which itself depends on that value of j. But of course, it only depends on it prior to the loop. So we basically are going to have some kind of variable k that starts at j and only goes until it's equal to top minus 1, which is n minus j minus 1. And the work that happens in there is 1, 2, 3. So at this point, I've actually solved all that I need to solve, and it's really just a matter of back substituting until I can find out what kind of simple expression I can get, what kind of closed form I can get for t of n, the goal being to express t of n as a function only of n and some numbers. I basically need to get rid of these dummy variables, i's and j's and such. So I'll start by considering this guy, this sum runtime for goo. It's got a 2 in it, that's easy. And then I can factor out a 3, and inside there there's a sum of 1, going from k equals j to n minus j minus 1. That's nothing but 2 plus 3 times, and then I just need to count all of them. Remember that it's this times this plus 1. I'm sorry, this minus this plus 1, usually. So I'll go ahead and do that. It's usually n minus j minus 1 plus 1. Now we do need to be a little bit cautious here because there's actually something kind of tricky going on in the code. Notice that under certain circumstances, the loop will not actually happen. Namely, when j gets up to top, and top itself is going to be smaller and smaller for different values of j, so that sometimes this loop won't actually execute. We had this expression here, and I was unwinding it to get a 2 plus 3, and then I have this minus this plus 1. Unfortunately, the denominator here is k equals j, not 1, so I made a little mistake there. Okay, and I also left off this minus 1. So what we end up with is 2 plus 3 times, and these 1's cancel out and we get n minus 2j. But I want to point out right now that this right here actually evaporates because, in fact, we don't do negative work, which would happen if this ever became negative. When n minus 2j gets to 0, in fact, this loop isn't really doing anything. And so this sum is only if n minus 2j is bigger than or equal to 0, which is to say, if we now solve this bigger than 0, is solve that inequality, right, that n has to be greater than or equal to 2j, or j has to be less than or equal to n over 2. So for other values of j, this loop actually doesn't do anything, and we need to take that into account in a moment. So I've got my main expression. I've figured out t of g, and it's pretty simple, and I'm going to substitute it into there, but I have to remember this condition over here. So I'll rewrite t of n equals now 3 plus, and I'm going to actually start condensing some terms here. Here's a 3, and if I count how many of them are, that if I pull the 3 out and I do the sum, it's just 3 times n minus 1 minus 4 plus 1. N minus 1 minus 4 plus 1. This minus this plus 1 is how many there will be. Plus this TG sum, okay? And that TG sum is still within here. So it's I equals 4 to n minus 1, and the TG sum is this whole thing over here, 2 plus 3 times n minus 2j. I think I'm running off my page here, so I got to be careful. Let us do a little bit of algebra. We get 3 plus, and here we get 3. We have n minus 5 plus 1. That sounds like n minus 4 to me. Plus, and I can reduce this little sum here too. That would be 2 times n minus 1 minus 4 plus 1. So that would be n minus 1 minus 4 plus 1 plus this whole sum, this whole sum, which I haven't done yet, 3 sum n minus 2j. So t of n then equals 3 plus 3n minus 12, I'm multiplying it out, plus, here I've got 2 times n minus 4, and here I've got 3 times this tricky sum, which I now need to think about a little bit more carefully. This tricky sum usually goes from j equals 4 to n minus 1, but I set up here that in fact there's a tighter limit on it, that in fact j has to be less than n over 2. So in fact, this sum here, which I'll do separately right here, really needs to be n minus 2j, but my j is more limited than I said. It actually can only go so big as n over 2. Okay, that's this limit here. So, taking that constraint into account, I now can actually just solve this sum, and this term doesn't depend on j, this term does, so I'll use my usual tricks. 3 times here n over 2 minus 4 plus 1, and over here minus 6 times, and now I got a sum on j, going from 4 to n over 2. Okay. And now it's really just a matter of continuing on with my algebra. I'll give myself a little bit more space. And over here then I get 3n over 2. That'd be a minus 3, which would turn into a minus 9, sorry. And here, minus 6, and this kind of complex expression, using the Gauss rule again, I would get n over 2 plus 4. That is, each term would be that big, and I get half that many terms, which is just n over 2 minus 4 plus 1, all over 2, because I only get half that many terms. Okay, so I'm just counting the number of these I get. We'll go back to the Gauss onion idea. And now it's really just plug and chug, but it's pretty easy to make mistakes. Minus, now this 2 will cancel that, and I'll get a 3. And so now this here will just be a minus 3. I'm actually going to do this polynomial now, n squared over 4 plus, and I have a minus 12. I've got a 2n here and a minus 3 halves n there. I think that's an n over 2 minus 12. And all of that was in fact simply, let's see, trying to, this expression up here, so I actually need to add in this material here to get my final expression. So, let's see if I got any more room here. I guess I'll go over here. I still have a little room I can see over here. So my t of n equals, I'm going to grab all this stuff, 3 plus 3n minus 12 plus 2n minus 8, I multiplied that as I went, plus this stuff, 3n over 2 minus 9, I'm going to continue, minus 3n squared over 4 minus 3n over 2 plus 36. And now I just have to gather together terms, which should be interesting. One thing here I'm really curious about is what kind of n squared terms I'll get. Okay, I got a little concerned when I saw that I have my biggest n squared term is negative here. So I looked back and I recognized that I screwed up right about here. You can see that I lost an n squared term, which is really not a thing I want to lose because negative n squared would give me negative work, and I know that just can't happen. So I see that over here, that when I did this multiplication, I had factored out to do the first term, right? So this is all of the sum of 3n, but I dropped this n, which I had factored out right there. All of this other stuff, right, belongs to the minus 2j, so that's a non-issue. But then I've got to bring this n forward because I lost it. And in particular, I lost it right here. And then over here, I thought that I had a minus 9, but in fact it's a minus 9n. Here and here. I have to fix it. Now let's come on over here. At this point I was doing all of those. Then I was bringing this one down. Here we are. So that should be 3n squared minus 9n. And now I've got all those terms. Now I can gather terms together, and I can see things aren't going to disappear quite so badly. So let's finish this puppy off. So our n squared terms, 3n squared and negative 3n over 4th. So that would be 3/4 n squared. Good. And now my n terms, I have an n, a 5n, and that's a minus 4n, and that's a minus 5.5n. And now finally my constant terms, 3 and negative 12 is negative 9, negative 9 and negative 8 is negative 17, negative 17 and 36 would be, what, 19? Okay, let me double check that one. I went through that one too fast. Let's see, negative 9, negative 17, right, 36 and negative 17. And yeah, good. So that's my final expression for the runtime. By the big O rule, I know that this term will be dominant and constants are omitted, so I can quickly say is O(n) squared. And not only that, as you can see, it's got a 3/4 in front, and that's a fairly accurate estimate. Okay, well that was pretty tricky in terms of algebra. Really, we had done most of our work here and here, although there was this one very interesting point, which I didn't see actually when I originally made this problem right here, this kind of constraint on the values of j that makes sense given this kind of trickier while loop there.